Welcome back to the navigation lectures in the course on drone systems and controls. We will be talking about global path planning. So, we will understand the role and importance of path planning in autonomous systems. First, we will talk about global path planning, then we will differentiate global and local path planning approaches. We will identify and construct different environment representations. We will talk about different representations of environment which are important and becomes useful in global path planning, and after that we talk about configuration space and how the obstacles are modeled within that. We will talk about implementing and analyzing graph based algorithms such as Dijkstra for shortest path computation, and accordingly we will coordinate with the real world applications for global path planning of drones. Fine. So, what is path planning? Path planning is a kind of a process of determining a feasible or optimal route for a robot or autonomous agent or a drone to follow from a start position to a goal position. So, just assume that the drone will start from this particular position and it is expected to reach somewhere at this final position or goal position, right. So, we need to find by path planning or path planning algorithms, what we want to see is that we need a path, a feasible path, so that the drone flies from the start location to the goal location, okay, while avoiding the obstacles in the environment. So, if there are some obstacles, buildings, then maybe electric poles, some bridges, any structures like that, those are to be avoided. If some other drones are coming, some other aerial vehicles are also flying in the same area or same environment, then those also should be avoided. So, path planning like ensures the safety of the drone and also mission completion. Fine. So, the key components of path planning is start and goal configuration. So, we need the positions and orientations of those. Then environment representation, we need map of the environment to know more about it, okay, map, then terrain information, then we need some constraints which are kinematics, kinematic constraints, dynamics of the drones, then safety margins are to be included. Then there will be some cost criteria like shortest path, then energy efficient path, smooth path, something like this. So, these are some kind of metrics to check whether the planned path by some path planning algorithm is satisfying or not. Based on that, the efficiency or credibility of the algorithm depends. Okay. So, why path planning is important? It is critical because it enables autonomy. So, when there is a manual control, the drone operator can send drone to the desired location, but when it is autonomy or autonomous flying or a drone, it is important that the path planning is inherent into the control mechanism of the drone. Okay. It ensures safety. So, safety and efficiency. Safety means what? It should be avoiding the obstacles, it should not get collided with the obstacles in the environment or other aerial vehicles. At the same time, it integrates perception, control and decision making module. So, perception are the sensors or sensor modules which will sense the environment, and then based on that the control mechanisms will be designed and finally the decision will be taken. Fine. Okay. So, it is a kind of foundational concept for advanced tasks like surveillance, rescue missions, etc. Okay. When you are sending some drone for surveillance of a disaster affected location or something like that, then the drone should be able to avoid the obstacles present in the environment. If it is not doing so and gets collided, then the mission will not be accomplished. So, safety is important for the drone, that we have to think about, and efficiency, being efficient in finishing the mission in whatever it is meant for should be accomplished in given time, and the drone should be safe. Okay. So, we see that there are certain domains like mobile robots, then drones, self driving cars, manipulators, multi robot systems, which are the autonomous systems for which path planning is very important to navigate into the cluttered environment, to maintain safety, to avoid obstacles, to plan trajectories, to track the planned trajectories, then to move from one pose to another, then having efficient smooth paths from one point to another point. So, everything, all the aspects which I am talking about depends on efficient path planning, so that it gives safety and efficiency to the drone. Okay. What is global path planning? It is a process of computing an optimal or feasible path for drone from start location to the goal location. So, it should be optimal or feasible depending on the other constraints like the physical constraints of drones, etc. Okay. To move from a start location to goal location while avoiding the obstacles, in global path planning we need a known map. That means, if this is the environment and we need to move from the source to goal location, we should know the environment properly with a map, so that we know where the obstacles are, where the buildings are, where the electric poles are, fine. So, those things are important, and accordingly it should be taken into consideration while designing the path planning algorithm. Okay. It has a difference with local path planning. Local path planning happens in real time. That means, when the drone is flying from one point to another, but it is not knowing the existence of all the obstacles, all the buildings or structures. If the map is completely not known, then when there is some obstacle, it comes as a surprise to the drone or the sensor system of the drone, then it needs to plan its path in real time to avoid the obstacles. Okay. So, that is called local path planning. In global path planning, we assume that the map is known, we know the system very well. So, we can design or prefix the trajectory from the very beginning. Environment is static, because if it is dynamic, then the known map will not be there, and for that a real time planning will be required to avoid the obstacles. So, that comes under local path planning. Okay. And also in global path planning we assume full visibility, fine. So, when we differentiate between global and local path planning, we see that in global planning, route planning is happening before the mission. It is a known map based exploration, fine. Like delivery drones, we know the map of the environment, and we know from where the drone will start and from where it will drop the items. So, it is a map based exploration, and long range navigation is possible, because it actually maps the entire path from the source to goal location. Now, when it comes to local planning, it is mostly focused in drone navigation or autonomous vehicle navigation into obstacle avoidance during movement. It can handle dynamic obstacles, or if the map is not fully known, that also can be handled, and local path planning happens for a shorter range. Global path planning is from, if this is the entire environment and this is the source and the drone needs to go here, which is the goal, global path planning takes care of the entire route. However, the local planning will take charge or will handle the situation when some unknown situation is happening here. That means, some obstacles are lying here which are not given in the known map. At that point of time, the drone can't go through the obstacles, and it should take some maneuvering movement and then again get merged into the maybe the prefixed trajectory. Okay. So, the local planning happens only at this part, where it is a kind of dynamic replanning of the path, and then it happens in real time and generates the trajectory to maneuver. However, global planning is from the source to goal. So, it is long range navigation and local planning is short range. Okay. So, in global path planning, map is known, whole path from start to goal is known, obstacle is known, positions are known in advance, computational time is higher because it plans for the entire route, poor in dynamic environments because it depends on the known map, path optimality, since it is prefixing the path based on the known map, it is optimal, and usage timing, it is computed before the mission starts. Okay. However, for local path planning, we have some dynamic scenarios involved in the environment, or the map is partially known, not entirely. Okay. It happens for short term, immediate next step decisions are to be taken here. Obstacle handle, once it is detected by sensors, then it can take care of the obstacles in real time. Then computation time comparatively is lower because it is for shorter range duration, but depending on the algorithm it can be complex. Okay. Adaptability, it is excellent for dynamic or reactive behavior. That is why when we are doing for local path planning, sometimes it is called reactive path planning also. Path optimality, it prioritizes safety or reactivity, or like focuses on reaction time. As soon as possible it can take a maneuvering movement like that. So, those things are more important, that is why it prioritizes safety, reactivity, everything over optimality. So, for local path planning, if we do not get the optimal path, it is still fine, but safety is even a bigger concern there, because we want the vehicle which is for some purpose trying to conduct some mission remains safe. Okay. And this execution is done in real time. So, during execution we do local path planning. Okay. We see one example scenarios where it shows that the drone starts from here and we are having known obstacles. So, it plans a path to reach the goal. So, just assume that it is a delivery drone, it calculates the optimal route across a city from the warehouse to the customer center or customer house using some satellite maps which is known, and this is pre-planned. So, before the delivery drone even starts from this location, this path is decided, it goes like that, assuming there are no dynamic scenarios, no change in the environment, and whatever map it is knowing is not a partial map, right. But when comes local planning, then while flying, if the drone detects a building or tower which was not in the map, or the map was with partial information, then it should take just see if there is some obstacle here also, then the drone can't go like this, it needs to take another maneuver here, something like that, right. So, a drone detects a building or tower in its path, then it needs to adjust its path in real time, fine. Now, when we combine the use of global and local planning, that is what a drone does, or the drone control system is designed in that way, that it uses global planning to plan the course to the destination or goal location, right. Now, when it like encounters some obstacles or some unknown objects or some other aerial vehicles inside this particular environment, it in real time reroutes. Okay. So, local planning is done kind of dynamically. Key concepts in global map: complete knowledge is required about the environment. Static obstacles are assumed, that is why in known map we know that where the static obstacles are there. Okay. Optimality, it tries to find the shortest, safest or most energy efficient path in like its usual way, and it is done offline, not a real time computation. So, path is computed before the actual movement begins, fine. Now, applications in drones. It is used when the drone is navigating between different waypoints from start to the goal location, avoids no fly zones, obstacles, plans a fuel efficient weather aware routes. In agriculture, this global path planning is done, a global coverage path is planned to survey a field. Then common requirements are accurate mapping of the environment, efficient computational algorithms, that is very important. Also, you should have the computational capability into the drone or onboard computer, and integration with motion and sensor systems. Okay. Now, when we represent the environment, it can be represented as occupancy grid map, which tells that if you see this particular figure, it is environment is divided into grid like uniformly sized cells. Typically, when it is occupied, that means here it is occupied by some obstacle. So, we give a probability of say 1, or we denote it as a binary value 1. When it is a free space, we tell it 0. It is simple to implement, suitable for occupancy mapping with sensors, because in this way having the known map is easier to handle. However, the problem is that high memory usage are required and precision is limited due to resolution. Okay. Then the second kind of representation of environment is topological maps, where this kind of graph information are given. There are nodes which are important places, say rooms, intersections, warehouses, something like that. Edges are possible traversable path, and it is assumed that no obstacles are lying on the edges, right. So, what are the advantages? Efficient for large scale environments, representation is compact, it shows the entire mapping, that how it can be like the vehicles can traverse from one point to another point based on the nodes and edges. However, it is less detailed and needs higher level of understanding, semantic understanding. Another very important and useful representation is geometric maps, which uses precise geometric shapes of the obstacles. Okay. Now, you see here is it is a triangular obstacle, here it is a kind of rectangular in shape obstacle, and here it is a circular obstacle in 2D. When in 3D you can just think about the shape of the obstacles, then the circle what we are seeing here becomes a cylindrical obstacle, like that. Okay. So, often it is used in combination with drones, kinematics and dynamics. So, those constraints are also incorporated. It provides high accuracy, because now you can see that what kind of obstacles in which shapes are located where, and it is suitable for continuous space planning. However, it becomes complicated. Generation is complicated, and then again we have to work on that. Okay. So, how to choose a map? Which one will be using, grid map or topological map or geometric map? So, precision wise geometric map is better, memory usage happens very high here. So, it is a sometimes problem. Okay. Then grid map is better for indoor navigation, topological map is for large scale mapping, and geometric map is for precise manipulation. Okay. Algorithmic support, we get A star or Dijkstra algorithm for grid map, graph traversal methods for topological map, and sampling based methods like RRT, RRT star for geometric map. Okay. Now, we will briefly talk about configuration space, which is a space of all possible combinations or orientations a robot or drone can assume. Each point in configuration space represents a unique configuration of the robot, like its position, its orientation, angles, etc. So, configuration space is like kind of, it shows the robot's geometry or drone's geometry, movement capabilities from the workspace into a mathematical space for planning. Okay. So, the key idea is that it transforms the planning problem from a physical space what we see to a mathematical space that considers the constraints from the drone or robot side. Okay. So, configuration space shows all the possible configurations, what is happening inside the space. So, a set of configurations where the robot collides with obstacles is or obstacles are present is given by this particular set. This particular set gives set of collision free configurations. Okay. So, why to use configuration space? It reduces the geometry to a point in high dimensional space. Then it allows obstacle expansion instead of robot expansion. We can see it not in physical space, but in transcended mathematical space, and it enables efficient planning algorithms to be used. Okay. Yeah. So, this is a geometric map which gives a very close representation of configuration space, where we can see what kind of obstacles are there, which spaces are occupied by the obstacles, which are the free spaces, etc. Okay. Now, we will talk about a concept called graph based search algorithms. What happens here? It is a global path planning. What is graph? A graph will have some nodes and edges. Nodes are the positions or important positions, edges are the possibly traversable path. So, global path planning involves searching a graph that represents the environment. Okay. How we will be seeing in the example. So, it will be having, since we are talking about graphs, it will be having nodes, then from one node to another node you can or the autonomous vehicle can traverse through the edges, which are the feasible paths or traversable paths, something like this. fine. Okay, the algorithms explore this graph to find optimal path from a start location to a goal location. Just assume that this is the start location and this is the goal location, then how to go from this particular node to this particular node. If it is not, if it is connected, then we have the path. If it is not connected, then we have to take some interconnected edges. So, which is the shortest one, which gives the shortest distance. So, that is the objective of search algorithms, and some common graph based search algorithms are Dijkstra algorithm and A-star algorithm. Okay. So, in this lecture we will talk about Dijkstra algorithm. What happens here? We find the shortest path from a start node to other nodes in a weighted graph. Okay. It was developed by E.W. Dijkstra in 1956. The type is a single source shortest path algorithm. So, for this particular algorithm we have a single source point or node. We have a graph with vertices V and vertices or nodes and edges E. Okay. One important thing is that the edge weights should be non-negative and there is a start node S. What we get out of this is a shortest distance path from S to the other nodes and the corresponding shortest paths. Okay. Fine. So, you see in this image that we have this particular graph where A is the root node or start location and G is the goal location. Now, we are not having any direct path from start to goal location. So, we need to take the interconnected edges. Now, these are the edge weights which tells the kind of representation of distance between the nodes. Based on this information, we have to derive the optimal path, and Dijkstra algorithm helps in doing that. Okay. So, the key idea is that we need shortest distance from start and then iteratively it expand the closest unknown node. It will be clear in the example. There will be certain distance array which stores the shortest known distances, then there will be a priority queue which extracts node with smallest tentative distance, and there will be some previous nodes, that means the nodes which stores previous node on the shortest path for reconstruction. Okay. So, we have to initialize the algorithm with these two parameters where when we start, this V is not same as the start node. Okay. S is the start node, V is anything other than this S, okay, and all nodes are initially unvisited. Fine. So, other than start node, for the start node the drone is already there, that is why the distance is equal to 0, and it is taken that all the nodes initially are unvisited and it is considered that all these nodes V not equal to S, the distance is infinite. Okay. We will see it in clearly in the example. So, it uses like guarantees optimal shortest path for non-negative edge weights. This is the time complexity and works on directed and undirected graphs. However, it cannot handle negative edge weights, as I told that is the preliminary assumption for Dijkstra algorithm, and it is slower than heuristic based algorithms when a goal is specified. Why slower will be clear in the next lecture when we talk about A-star algorithms. Okay. There are different applications in network routing, robotics, global path planning, drone based systems, GPS navigations of aerial systems or robotic systems, and some other game based AI for shortest path finding. Okay. So, we see one example here. This is the same graph I was showing at that point of time in the previous slide. So, we have A, right. Now, this is the start node. So, the distance is 0, fine, and all the other nodes are unvisited nodes. So, the distances are taken as infinite, unvisited, fine. Now, what happens in the next iteration, from A, the drone or robot can go to two nodes B and C. So, B has a path cost to reach B from A, the path cost is 4, and to reach C it is 1, And what is Pn? Pn is the proximal node. That means, for C and B, both the nodes, the proximal node is A, previous proximal node, fine. Okay. Now, A is 0, B path length or path cost is 4 and C is 1. So, we tell that now coming to C is a better option, fine. So, you see now C is included in the path. When I am showing the like nodes in green, that means it is being considered in the shortest path. Okay. Now, it comes to C. After it comes to C, there are two paths, one is to go to D, another is to go to F. So, if it goes to D, the path cost is 3, if it goes to F, it is 7. So, which is better? D. So, D becomes green, fine. Now, from D it can go to B, but already it has come from it has rejected B and come to C. So, from D what it can do is that it can go to E, right. Now, if it comes to E, then the path cost is how much? You see, it comes as 1 plus 2 plus 4. So, total 7 starting from A, fine. So, and that is the path. So, it E becomes green and it gets included in the shortest path, fine. Now, after E, it is the shortest path is coming to G, right. So, what is the total path cost? 1 plus 2 plus 4 plus 2. So, total 9. So, we see that now G comes in the shortest path, right. So, the final shortest path is going to be A, C, D, E, G. Okay. So, first it will come to from A it will come to C, then it will come to D, then it will go to. So, it is the path, this is the shortest path. Right. Okay. Fine. So, there are some other common algorithms which are used in global path planning. Dijkstra is something which we have already talked about, and based on this Dijkstra algorithm we can plan for drone path planning, but it has certain limitations. Then there are some other algorithms like A-star algorithm which includes heuristic, and for that the process becomes faster. Then Dijkstra and A-star both are graph based search algorithms. After that what we have is sampling based algorithms RRT, then RRT star, PRM and D star, something like this. So, these are the common algorithms which are being used in global path planning of the autonomous vehicles, and based on this we can, depending on the specific application, we can choose the algorithms accordingly, it will give the results of path planning. Okay. So, the idea is to get a safe path and mission completion. So, in global path planning the drone should be safe, it should not collide with some obstacles, and at the same time it should reach the goal. These two are the important criteria. Okay. So, global path planning uses a full map or known map of the environment. It contrasts with local path planning which is done in real time. Then common map types which are in like used in global path planning are occupancy grids, topological maps, geometric maps. Graph based algorithms, we talk about Dijkstra in this lecture, A-star in the next lecture, and Dijkstra algorithm guarantees shortest path using edge weights and a priority queue, but it is important that the edge weights should be positive, non-negative weights are not. Okay. So, the next lecture will be on A-star algorithm. This is a MATLAB source of using this particular thing, graph based shortest path algorithm. You can see this one so that it helps you in coding Dijkstra algorithm. Thank you. See you in the next lecture.